Okay, here's the thing. So last week I have explained to you about fixed law, and today I'm just gonna continue with um, explaining about the theory of our mass transport. And on Friday, we're gonna have examples and also practice. Okay, and wait. Okay, yeah. Uh, and on Wednesday, next Wednesday, we will have equation of change again, a theory. So we actually need 4 hours to for practice or something. Um, so Kevin, have you uh, can you suggest a time, or is it the time is too soon for holiday?
When, Bu?
I don't know, but
Uh,
I will ini mudik ya on Wednesday afternoon.
uh, okay. Is it okay to do it next week, Bu? Or do you want it like 2 weeks in Lebaran break, Bu?
No, I don't want you.
Okay, so it's better to do it like around next week, Bu.
Yeah. Maybe if you still have time on Tuesday, do you have time? Yeah.
I need to discuss with the whole class, Bu, because some of us are having pembi akhir from lab as well on
Right.
Tuesdays,
Okay.
Bu.
But if not, then what I will do, I will maybe make a video and also give you some assignments to you, okay? Uh, and then, and after that, if you think you need to do, if you want to discuss the results of the assignments or to have a discussion like one by one, like I always did before, we can do it after Lebaran. Yeah? How about that one? Okay, yeah, or maybe the alternatively I will make a video about some examples, and also I will give assignments to you, and after that, uh, after maybe after Lebaran, or yeah, we'll see the time before UAS, and then we'll have maybe one session about uh, examining, or explaining the problems. Okay. Okay, we'll talk it later. Okay, so today let's continue on our talk about fixed law. Okay, so fixed law is all similar with yeah, it is in uh, the momentum transport. It is called similar to Newton's law of viscosity, similar to the Fourier's law for energy transport. So the fixed law. Wait. Why? This one is not. Okay. Yeah. So, oops. Yeah. So the fixed law describes the quantification of mass transfer of component in the mixture. Okay, and then we know that the mass transfer corresponds to driving force, which is the concentration gradient, and also refers to its distance. So we know that the fixed hukum fixed law number one is, we call it J. A capital J is for molar base, and a small j is for a mass base. Okay, so weight base, something like that. Okay, and then so here the ja, so here we call it a ja equal to dab, and then multiply with the dca over dz. Yeah, so this one is the driving force. Let's say you have one concentration in with some concentration, and then you have another room that you don't have no concentration of A, let's say, and then you want to find the rate for mass transfer from the molecular transport from one case to that one. It is called the delta concentration. Okay, and Z is the distance between the 2 points. Okay, And D is the diffusivity, yeah, diffusivity between two substance. This is the gas, the binary gas diffusivity. Or if you want to, sometimes we also didn't write the concentration, like how many mole per liter or how many, but we often just do the X, yeah, or the mole fraction. Okay, so if we have a mole fraction like this one, so what we need to do, we have to find the concentration of the mixture. For example, the concentration of the mixture gas in the system, how many, for example, how many mole per liter or something, and then multiply with the dx over dA. Okay, so this actually tells you about the rate for transport of the component A in the mixture of component A and B molecularly, ya, secara molekular. Okay, so in this case, we use stationary media or just medium diam. Okay, just let's say, I don't know, for example, you have air, okay, you have or air, and then let's say it's just the component of air is, for example, let's say there is a room, and then there is air. The air contains oxygen and nitrogen. So oxygen is the component A, nitrogen is the component B. Okay, and then in one point you open up tabung gas, yeah, the gas bottle, for oxygen gas bottle, and then you open it with some concentration. So you have concentration in one point, and then how is the rate of transfer of that oxygen from the gas bottle throughout the throughout the area. Okay, it would be the rate of transport. Okay, later on you can find a Fick's law as well, in maybe for the application, for example, for safety. Okay, if you have a hazardous gas, if you have leaking of hazardous gas from one point, and then how fast it can travel from that, for example, chemical plants to the surrounding, it is based on the mass transport. Okay, and then
Bu,
yeah.
sorry Bu, I wanna ask Bu, what is the WA and XA again Bu, and how does it relate to, like, for WA
This
the
one,
row and XA and to C, yeah? Sorry Bu.
this one is mole fraction. Yeah. Sorry, this one is mass fraction. Yeah. Yeah. Got it? So, okay, maybe, wait. Okay. So yeah. So here's the things. You can you can have everything in a mass unit, or you can have it in molar unit. If you use a mass unit, then for the concentration you use rho, yeah, density. Okay, so this is the mass of the gas divided by the volume, let's say. Okay, so for example, the mass of the gas, and then you can use the PV and RT, to get the rho. Okay, and then yeah, and then you can use, for example, for the gas you can use P and RT, yeah. So then you can find this is equal to M divided by MR, let's say. So then you can find your rho, that would be PMR over here. Okay, like that. Okay, so at least the sense of this for the mass transfer, if you have the the amount or in a mass unit, and then divided by the volume, and then that become rho. Okay, so this is but the rho is the rho of the mixture, the density of the mixture. It may be contained of the density of A, and then plus the density of B. Okay, so let's say the density of oxygen is 0.2, and then 0. Kilogram per cubic meter, and then this one nitrogen, let's say 0.8 kilogram per cubic meter. Then the rho or the density of the mixture or the air, for example, equal to 1 kilogram per cubic meter. Okay, So okay, let me write it. Let's say example. This is not the right one, yeah, but at least you can have area. You can have some idea. So for example, this is the A and this is the B. For example, the row A is 0.2 kilogram over cubic meter, and then row B is 0.8 kilogram of cubic meter. Okay, around that value, and then so the row would be row A plus row B, yeah, 1 kilogram over cubic meters. Okay, however, can you guess how much is the mass fraction of the A? Of course, it is 0.2 divided by 0.2 plus 0.8, yeah. This is okay. So the omega is actually row A divided by row A plus row B. Similar with XA. XA, or in mole fraction, is actually the concentration A divided by the concentration of the mixture. Okay? Got it?
Okay, Bu. Kind of get it now.
Yeah. So yeah, similar with concentration, but it is in molar unit. So if you want to get the molar unit, then means if you want to convert this one to that one, the molar unit should be N over V. Yeah? The number of mole divided by the number of mole divided by the volume, for example, for the gas. Okay, while the raw would be P multiplied with the MR, yeah, the molecular weight of the divided by RT. Okay, so that's why okay, so here if you use the molar basis, this is you use concentration. Okay, if you use a mass basis, you use mass you use density. Which one do we use? We often use the molar one. Yeah, we often use the molar one. But if you think about it in if you remember about absorption, yeah, about absorption unit, or yeah, absorption unit, we use the mass basis. Okay, so yeah, we use the mass basis. But in molar, in our examples, in a few and maybe on Friday, I will show to you that we will use it on concentration basis, on yeah, on the molar basis. Okay, so this one is when the medium is stationary, medium diam. Okay, this fixed flow JA is similar, maybe analogy, I can say the analogy is similar to can you guess what is the similar with the momentum transfer? What unit, what quantity that's similar with on the momentum transfer?
Like tau, Bu.
Yeah, tau. And this is actually similar to what for in the heat transfer.
Q, Bu.
Q. Okay, yeah, so this one, so this also similar, the tau yx equal to minus mu dv x over dy. Okay, q x equal to minus k dt over dx. Okay, this is ja equal to minus dab dca over dz. Okay, so if you can understand the similarity between all of them, I think to learn about mass transport would be much easier because you know the mathematics, you know, everything's the same. Okay, see, this one is the gradients, right? The driving force and also the distance, right? This is the driving force and this is the distance, driving force and distance, driving force is the distance. And this one is the DAB, mu and K is the, we call it resistance, yeah, resistancy. So if you have higher value for conductivity, for mu, for viscosity, for diffusivity, your rate would be higher. Okay, your rate of transfer would be higher, which is in this case is the rate of mass transfer. This is we call it a shear stress or the rate of momentum transport, and this is the rate of heat transport. Okay, any question up to here? No. Okay, let's continue. Okay, the second one, if you remember in the previous one, in the momentum transport, heat transport, we know that there is a molecular case and also there is a convective one. Okay, there is the molecular. Oops, wait. Okay, so there is a molecular, and there is a, we call it convective. Now let's talk about the convective side. Okay, pergerakan campuran, convective side. Okay, so if the mixture is moving. Okay, let's say if you're on the inside a train, you know, this train is still just stationary, masih diam keretanya, and then you walk from the last car to the front one. The rate of you moving is your Fick's law number 1. Okay, itu medium diam. So the media or the train is stationary, and then you just walk with some rate. Okay, from the with some velocity. Okay, with some velocity. So you can calculate how much is your velocity. Let's say 4 kilometer per hour. Let's say. Okay. And now, what happened if we actually moving from the last cart into maybe the first cart, dari gerbong paling belakang sampai gerbong paling depan, but then the train is also moving. So that means the media is also moving. Okay, so if we think that the media is actually another component, okay, and then this also have a velocity, okay, which VB, and then so in let's say the component A is moving with a velocity of A, so it's also moving. Yeah, this one is moving. Okay, maybe the first one in this case we can call it the medium is stationary. Let's say you have water, the component B. So for example, you have water, component B, and then you have sugar, and then you put in some water, you put a drop of sugar in here. You didn't do anything. Okay, but over the time, okay, this will it will start to disperse, and this disperse is calculated by Fick's law, this one. Okay, you see this is the concentration of Ca in 1, which is maybe very, very high, and this one the Ca in the beginning maybe, I don't know, maybe finally 0, for example. 0, for example. So of course, because there is a driving force, then the transfer will, so the mass transfer will occur, and you will have later on, after a few minutes, this area will also taste sweet because the sugar has transferred from here to there. Okay. Now this one in a mixture, here you have both A and B is moving. Let's say you have the first one, you have your sugar here, and you have the water here, and then you stir it, yeah, you stir it with a spoon, okay, and then of course the sugar will have velocity, the the water will have velocity as well, okay, they will and then you stir it, okay, of course, and there would be velocity, okay, and then the velocity is a vector. Remember what is the vector? When if the vector, you have the quantity, and then you have also direction, okay, so the direction, kecepatannya, arah, the direction is different, okay, it can be similar, it can be in a similar direction, it can be in counter current, in reverse direction, it can be also, okay. But however, we can find the medium, we call it medium velocity, or the mixture velocity, kecepatan campuran, which is the mixture would be the average velocity of A and velocity of B. Okay, and then how to find the average velocity, kecepatan rata-rata. Okay, so how to find the average velocity? We can use just similar, the similar formula, yeah, which is the velocity of A multiplied with the concentration of A plus B multiplied with concentration of B, and then we divide it by concentration of A, concentration B. Okay, this is the average velocity, and then we can call it, maybe we say that the molar average velocity is, we call it V star dash, and then the mass average velocity is V dash. Okay, so this one. So once we know the molar average velocity, so how to find the real, the real component, berapa kecepatan sebenarnya relative to stationary, okay, dengan dasar diam. Okay, so there, so if we have the component velocity, let's say VA and VB, okay, and the medium velocity, let's say it can be V for, let's say V is for mass, and this one is for a molar basis. Okay, so the velocity of the components, okay, the velocity of the component I, which is the true one, is actually the velocity of itself, minus with the velocity of medium. Okay, let's say if I have the for example, I walk from one cart to another cart. Let's say I have 4 carts in the train. Okay. I want to know what is my velocity. Okay, how much how fast I walk from the last cart into the first one. Okay, the observed medium, kecepatan medium, okay, is actually for example 100 km per hour. Okay, okay, so for example that one there, but however the component I, the initial one, is actually what we want to see is actually this one, berapa dia jalan lebih cepat. Okay, so which is maybe this one. So maybe this one is only so we're not if we started from, let's say, from Kota Bandung, yeah, our relative velocity if I walk is not 100 km per hour, right? But it should be maybe only 1 km per hour. Okay, so this actually tells you that the component velocity, it should be based on the stationary basis ya, acuan diam, kata dasar acuan diam. Okay, this one. Okay, now but don't be confused, we're gonna move on to the next slide, so we will see. Okay, so what does it means, okay, of this one? So what does it means, what this one? So maybe wait a minute, I'll explain one more. Okay, so here we called it we called it molecular flux, molecular, okay, which is the the substance itself, both of them is stationary, diam, okay, and then but the flux at dasar acuan diam, yeah, the flux which is the based on the stationary, we call it NAZ. Okay, and then if you want to see the NAZ, N is small, again for the small number, small alphabet is mass flux. The capital one is for the molar flux. We often use the molar flux. Okay, so so here the Fick's law is actually molecular flux. Okay, however, we know in the reality we have moving, we have velocity. Okay, so we have to find the correlation between NA and GA. Okay, so this is also molar flux, this is also molar flux, but this one is only for the molecular one, but this one will include those velocities. So how to get that? Okay, so the flux is actually, we can call it, the flux is actually the concentration multiplied with the velocity. So the flux is actually the concentration, which is, let's say, maybe Ca, divided by time, divided by area. Okay, that is flux. This actually equal to the concentration. Yeah, the oh, sorry, not concentration. This one is not the flux, is actually the number of mole. Yeah, which is okay, let's say, okay, and then it's actual to the concentration. This is mole divided by volume multiply with velocity. So velocity is distance divided by time. Okay, so let me write it up to here so you can maybe one more. So flux equal to concentration multiply with velocity. So the concentration is so the flux is actually the mole, yeah, which is the mole of the substance divided with the area. Flux is always divided by the area, the rate of mole, so it should be is divided by the time, and then divided by area. Area, let's say, or maybe I think it's better if we call it with the unit. Yeah, I think it's better if we call it with the unit, so we can easy to write. Okay, so let's say this is the mole. The area is meter square, let's say, and then multiply with the time. Okay, and then the concentration is actually the mole again, divided by the volume, right? The volume is cubic meter. And velocity is the distance divided by time, or divided by the time second. So if we cancel this out, this become m. Okay, so we can argue that even for the molar flux or mass flux, flux is actually concentration multiplied by velocity. Okay, now because the phenomena now include velocity, let's include the velocity into this J. Okay, so sorry, it's not that one, but to this one, to the N. Include that one, the console. So N, so the N, which is mass flux, I don't know what is the English pada dasar diam, is equal to the concentration A multiplied the VA with the concentration of the velocity of VA. Okay, this also sorry, this is not the mass flux, molar flux, yeah. Okay, got it? So okay, so here molar flux multiplied the velocity. This one is the molar flux if it is include velocity. Okay, what is the difference between the that one, the fixed flow? The fixed flow is when all of them, both A and both B, is stationary, diam. Okay, so they will just moving because of there is a molecular transport. But in this case, we know that we know that the component A has a velocity of A, component B has velocity of B, so we define the flux as a concentration multiplied with velocity. Okay, in other words, okay, in other case, we also know GA or this one here, which is the velocity, which is the concentration multiplied with the velocity of the substance with the base of the stationary base, yeah, pada dasarnya. Okay, so because this one, so here we have correlation between JA and NA, which include this one. Okay, so here so we need to find the correlation between JA and NA. Okay, so in a sense we find that JA, okay, so this one we have that the NA from here, this one. So maybe I can write where is this coming from. Okay, by substituting by substitute this one to here. Okay, by substituting this one to here, we actually find that later on we find that the NA would be equal to JA plus XA and A plus NB. Okay, which is A is the component A and B is the component B. Okay, so this one, this is the correlation between the JA and NA for the this one is for mass basis. This one is for molar basis. Okay. So this is called, sometimes we call it fixed law number 2. So fixed law number 1 is JA equal to minus DAB C dXA over what, I forgot, dz, yeah. Okay. And NA is actually So this is the molecular flux when you have velocity. Yeah, let's say just that the molecular flux when you have A and B has a velocity. Okay, this one JA plus XA multiply with NA plus NB. So that means we have to find the correlation between NA and NB. Harus tahu hubungan antara NA and NB. Okay, and then in the books, in the birth book, we call it this one NAZ, or combined flux, or we can call it combined flux. So the combined flux is actually, we call it N. Again, N is a flux, so that would be the mole of the rate, yeah, the mole, the rate, so that would be the mole per second, multiply with the area. So maybe the area can be cubic meter, can be maybe, let's say, cubic centimeter square, let's say that one, yeah. So this one is called the area. Okay, so the NAZ, or the combined, we call it combined flux, or the rate of the mass transfer of A to the direction of Z. Okay, this would be equal with the C, which is the this one is actually the JA. And then if you want to write the JA equal to this one, so DAB, multiply with the concentration, dXA over dZ, or this is called the molecular flux, yeah. And then this one is the convective flux. Okay, the convective flux, then you can see how does it means. Okay, so that means this tell you, because there is the NA and also NB, so you need to know the correlation between NA and NB. Okay, what correlation? Maybe I can give some examples. Okay, so this is the JA in the direction, yeah, in the maybe in the 3 dimension, dimensi ruang. Okay, with a 3 direction, just they just keep it. Okay, so maybe before we continue to the example, maybe I'll tell you some example here. For example, later on, okay, I'm just gonna explain you the phenomena. You can have a think, and then on Friday we'll continue with some explanation. For example, here I have maybe a Baker glass, or not a Baker glass, yeah, maybe a tabung reaksi, yeah, this one here, a tube, that one there, and then I have a liquid. Okay, the liquid is kept similar at Z equal to Z1 at any time. Okay, maybe Pak Mubiar, yeah, almarhum, explained to us before that maybe here there is maybe some reservoir or something, yeah, that keep this distance is just keep constant. Okay, and after that, let's say, or I have let's say the liquid. Okay, and here around here I have a gas stream, angin-angin, ya, kan? And the gas stream has a composition A and B. So there's a gas stream. Okay, so you know how much is the concentration in this area, how much the concentration in that area. So what do you think? What is the can you explain to me, maybe can you have an idea how is the direction, in what direction the mass transfer of A will go, in that area, or the upwards or downwards, or in what area?
I think mass transfer will be going upwards because of the evaporation of the liquid first.
Yeah.
Then
yeah.
after that, when it intersects with the gas stream, then it will go to the right.
Right. Okay. So yeah. Right. So this one, if you see here, you have a concentration in Z equal to Z1, and then in this concentration, you have maybe some other concentration which has a difference from here, right? So you have to do there is a gradient there. So of course there would be a mass transfer there. Okay, later on, to solve the problem, we have to find again, make a shell, yeah, or maybe a thin shell like this, and the thin shell is maybe with delta z. Okay, so if you think if we go back to the n, that one, so na equal to ja plus xa and a plus nb. Okay, so you may want to know what is the correlation between na and alpha and b, yeah, at later on. Okay, this one is gonna be different case. For example, if you don't have a moving over here, let's say, okay, and then later on, okay, in this area, okay, what do you think? Do you have na? Do you have a flux of A which is going upward to that one?
Yes, Bu.
Yes, you have this value. Do you have NB? Do you think the like, for example, you have air for the B? Is the B is moving around this area?
No, Bu.
No. Okay. So because B is not moving, so B, let's say the other area, which is the medium, the other medium in this area, because it's not moving, it's not forced by, you know, exhaust fan or something. It's not forced by blower or something. Yeah. Then we know that this equal to 0. Okay. So once you know that one here, you can calculate the this one, yeah, na equal to ja plus xa, that one, and then you can solve the problems, you know, and then find the boundary condition, and then you can solve it. So later on we continue on Friday. One more. Okay, so later on here there is the strategy again, similar. So again, always using mass balance, yeah, in the volume element, like that. Okay, there's another one. Okay, let's say for this one, we have a gas over here and we have gas over there. Okay, this is a gas A, this is gas B. Okay, and both of them is full with the A, so the XA is 1, so gas murni, yeah, the pure A. This also gas B, which is the pure gas. Okay, and then you want to know, maybe for example, remember about the that tube, and then you have those ammonia and also hydrochloric acid over here, yeah, and then you want this is vaporized, this one is vaporized. Okay, so if you think about this one. Okay, now if you think about it again, I'll rewrite the formula. Okay, so here if you have this is the like this one, yeah, the let's say if we open it there, we open the valve, and then the gas will move with this one is 1 mole, let's say this is also 1 mole. Okay, it will move to that way, it will to do that way. So what do you think? Do you have a correlation between Na and Nb? So the A would be in that direction, the B would be, of course, it will flow in that direction, right? Isn't it?
Yes, Bu.
Yeah, so here we have a correlation. We have to find the correlation between Na and Nb. So in the term of direction, the velocity, the direction of A would be, conversely of the NB, yeah, counter current. So then we know that, so that means in the value, the area, the the molar flux, yeah, not the mass flux, the molar flux, sorry, it would be conversely. Okay, once you know this one, maybe you can find the NA as well. Okay, that one. Okay, and later on this also a sublimation. Maybe later on we will see. For example, this is, let's say this is the A and this is the B. Let's say you have the the naphthalene ball, yeah, in your and then you hang it in your toilet, and then you just wait for a while up till it to do the sublimation. What do you think the correlation between okay, so what do you think about the B? Is the B has a velocity? The B is air. A is the naphthalene.
No, Bu, I don't think there's a velocity for B, Bu.
Yeah, if there's no velocity, then you can say that this equal to let's say a 0. But then you need to see again about the area, yeah, later on for the the mass balance later on. Okay, so this is just an example. Later on I'll try to find some more example on Friday, so at least you can have some more ideas before next week we move into application of equation of change. All right, looks like the time's up. Any question, maybe last question before we finish?
Bu,
Yes.
sorry, it's not a question, but can the recording of last week be uploaded to our next week?
Yeah, I will. So yeah, okay.
Thank you, Bu.
Last week and this week, yeah, and now, okay. All right, I think yeah.
Actually, I have a question, Bu.
Yes.
It's regarding the Fick's law where it's stationary, Bu. Like the constant D, which is the diffusivity constant. Can you explain about it, Bu? Like
Okay.
the phenomena within it and like the units.
Okay. It's actually I would actually explain it in the book, yeah, this one. But because in our course we focus on more about the mathematics, yeah, about how to solve the problems. But you can actually it is very interesting. You can see it on chapter 17 here. Okay, so the binary diffusion. So what is diffusivity? Okay. This one, yeah, this is called the diffusivity. So we actually measure it, and the diffusivity has a unit of centimeter square over a second, and then so it actually differ with any pairs. Let's say you have a CO2 and N2O, this diffusivity, but if you change it to another medium, if you change the B, you also can change this one. Okay, to calculate the DAB, there is a theory. We call it the theory of diffusion of gas in low density, and also there is a theory as well, like a physical theory. So maybe I can explain to you. Yeah. So this is really about diffusion. Is about how the 2-3 molecules collapse each other and something like that. Yeah, it's really about physics. Yeah. Kimia, fisika murni, yeah. So I just use a lot of this theory, Chapman and Schalk, and for example this one. For example, there's some assumption, and then if you know so between the two components, two molecules, there's some parameters here, and then you can calculate how much is the diffusivity. And yes, the diffusivity is a function of temperature. There is a temperature here, so I think we talk about diffusivity or the system still in the isothermal, yeah, with the similar temperature. But if you change with the higher change temperature, of course diffusivity also will change as well. Okay, but yeah, at least there. So it is a function of pressure and temperature. There is, I think that there is a correlation about that one if you want to see, but I think for the exam purpose, we will just pick up the value and then give it to you. But of course, you need to know how to get the diffusivity, and even all those bases. Which one? Yeah. Yeah, like this one. It's also it can be we can calculate it with experiments. So we calculate the rate, we calculate the concentration and the distance, and then we can get the diffusivity. Right? Okay.
Okay, Bu. Thank
Yeah.
you,
So
Bu.
you can maybe have a look around here, yeah, about the diffusivity. Okay. All right, I think that's all for today. So thank you for listening, and then I'm gonna see you again on Friday. I hope you can have a look on the examples that I put it in the PPT. It's also similar with the regular classes, of course. Then at least we can have yeah, to try to solve the problems, and also if you have any question, or and then even I can give some assignments, for example, yeah, or quiz maybe. Yeah, we'll see on Friday. Okay, thank you, and I see you again. Bye bye.
Thank you very much, Bu.
Thank you, Bu.
Thank you.